现在收看的是曹老师数学。
Black pen, red pen, yay!
In this video, I will show you how to find the derivative of an exponential function from scratch. And I will also talk about one definition of the special number e. And to do so, let me use this exponential function first, namely 2 to the x. And because we are going to do this from scratch, so to get the derivative, we will be using the definition of derivative in terms of a limit. That means when we have f of x is equal to 2 to the x, f prime of x will be, by definition, the limit as h goes to 0. And here we have that difference quotient, right? Namely, f of x plus h minus f of x, and then over h, like that. And now, to figure out f of x plus h, we can just plug in x plus h into this x, right? So this is the same as the limit as h goes to 0. And right here, we will have 2 to the x plus h, like this. Because once again, we're just plugging x plus h into this right here, right? And that's our new input. And then minus f of x, which is exactly just 2 to the x. And then over h, like that. And now, what can we do? As we can see, here we have two things adding together in the exponent, 2 to the x plus h. In this case, we can actually separate them, right? This right here is the same as the limit as h goes to 0. We can rewrite this by the rule of exponents as 2 to the x first, and then times 2 to the h. Because we know when we are multiplying and when they have the same base, we can just add the exponents. So 2 to the x times 2 to the h is the same as 2 to the x plus h. And we're just looking at this kind of like backwards, right? And then we have the minus. And let me write this 2 to the x in red as well, like that. And all this is over that h as well. And now what? As we can see, both of these terms on the top, they all have 2 to the x, right? So we can factor the 2 to the x out. And even better than that, because if you look at this limit, this is the limit as h goes to 0. It has nothing to do with x. So in this case, we can factor out 2 to the x all the way to the front of the limit, all right? And we will get, as I said, 2 to the x all the way to the front of the limit. And the rest is just going to be, we multiply by the limit as h goes to 0. And right here, on the top here, we have 2 to the h left, minus, we took this out to the front, but don't forget, we still have the 1 right here, right? So that's 2 to the h minus 1 over h, like this. And now, we just have to spend some time to figure out what this is right here. And if we can figure this out, we will be done, okay? And as you can see, if you just plug in h is equal to 0 right here and right here, we will get 2 to the 0, which is 1, and then 1 minus 1, which is 0. 0 on the top, over, plugging 0 on the bottom right here, we get 0 over 0. That means we have to do more work, right? So, what can we do right here? Well, in this situation, in fact, we are going to use a calculator to just investigate a little bit, all right? And to do so, I will just draw a table on the side for you guys, like this. And recall that when we have h is approaching to 0, you can just think about h is a really small number that's close to 0, such as 0.00000001, right, etc. And don't forget to do both the 0 minus and the 0 plus, because we have to figure out this limit as h goes to 0 from both directions, the negative side and also the positive side, okay? And as I said, we'll be using a calculator to figure this number out. We are going to plug in some numbers for h and then figure out this expression, 2 to the h minus 1 over h, okay? And just to save some time, I'm just going to plug in 4 numbers. The first number is, let me plug in 0.001 for h. It's pretty small, right? So I'm just going to plug in this number into this h and that h. And let me just set this up for you guys for one time, right here. This is going to be 2 to the 0.001 minus 1 on the top like this over that 0.001. And as I said it again, just use a calculator and then figure this out. And when we do that, we will get this is approximately 0.69339. And of course, you have slightly more digits after that, but these are the first 5 digits like this, okay? And you may be wondering, hey, this is not close to 0, right? So I'm going to give you guys another number that's even better. So it's a little bit better than that. So let me plug in 0.00001. This is closer to 0 than this, right? And pretty much do the same thing. And let me just tell you guys the answer. This right here is approximately 0.69315, okay? As I said, the first 5 digits right here. So you can see 0.693, the first 3 digits right here, it's pretty much the same. And the rest, or just change it a little bit, right? And you can imagine if you put in more zeros, yes, the first 3 digits will still be 693, and then maybe the 1 will be the same and things like that. But let me just leave it like this, because now I want to plug in some negative numbers. Let me plug in this value, but negative, okay? I'll put it down right here. This is negative 0.001. And when you plug in this into this right here, we will end up to have about 0.69291. And some more numbers after that, I don't know, but these are the first 5 digits. And I will do the same thing right here, but negative 0.00001, all right? So 40 right here after the decimal point, and then 1. But this is negative version. When we do that, we get 0.69314, and so on, all right? So as you can see, as h is approaching to 0, from the positive side and also from the negative side, this expression is approaching to 0.6931, right? Because as you can see, in fact, the first 4 digits are the same right here and right here. And you can try with more numbers for h, but as I said, this is about it. So you can kind of just make a guess for now. This right here is approximately, equal to 0.693. 1, all right? So let me just write it down like this. And the answer is pretty much equal to 2 to the x times this weird number, right? Once again, 2 to the x times this additional number, 0.6931. And now you may be wondering, okay, so what is this number? And is it possible for us to not have this number and things like that? Here is a really interesting observation. After we run through the definition of derivative, you see that when the function was 2 to the x, the derivative of 2 to the x, the function part right here, it repeats, right? We got 2 to the x right here as well. But the thing is that we have this additional constant. That's what I was saying. That is it possible to not have this constant so that exponential function, we can get the derivative of being exactly itself, right? That would be so cool, isn't it? Well, right here, I just, I chose the base to be 2. What if I choose the base to be 3? So let's just do that one real quick, right? And as you know, I'll just put down if my function is 3 to the x, okay? If I have this, then once again, f prime of x, by using the definition of derivative, and you can imagine this part will be the same, and similar, right? And you can factor out 3 to the x. And instead of the 2 right here, we'll get 3, right? And anyway, we will pretty much have 3 to the x right here times the limit as h goes to 0, and then 3 to the h minus 1 over h, right? Because once again, I just changed the 2's to the 3 because of this. And for this particular limit, you can do exactly the same thing that we did right here, plug in values and use a calculator. And let me just tell you, this is going to be approximately 1.0 9861, right? If you just plug in some numbers like this. And of course, we will still have what? We will still have the function part, namely 3 to the x being repeated from here to here. And we just have to multiply by this constant. And now, the interesting thing is that when the base is 3, this number is a little bit bigger than 1, 1.09861. And of course, we have a few more digits after that, maybe infinitely many, I don't know. But these are the first 5 digits after the decimal point. But this is a little bit bigger than 1. Is it possible for us to choose a base, a really nice base, so that when I put in it right here, this is exactly 1? Can we do that? Well, I chose 2, and it was 0.6931. And as I said, we have a few more digits after that maybe. And when I used 3, this is bigger than 1. So let's just maybe use about 2.5 for the base. So let me just like do one more right here. If the function is 2.5 right here for the base, right, to the x, and then we will pretty much have f prime of x equal to, and you know the function part will repeat 2.5 to the x power like this being repeated, and the base is going to be 2.5 instead of 3, right? So we have the limit as h goes to 0, 2.5 to the h minus 1, and then this is over h, right? And of course, let's figure this out by doing the same thing from a table like this. And in this case, we'll get this is about 0.91629, right? And as you can see, the function part will still be 2.5 to the x times this additional constant. So the observation is that when we have an exponential function, when the base is legit, all right, because we cannot have the base to be 1 or negative number, right? So for example, 2 to the x, the derivative of that, we get 2 to the x, the function part repeats. But it's just kind of too bad because we have this additional number. Likewise, for 3 to the x, we have this additional number. Likewise, for this, 2.5 as the base, we have this additional number as well. But one more observation. When the base was 2.5, right, this additional number is pretty close to 1, isn't it? This is just 0.91629 and so on. You can imagine, what if I use 2.6 and so on? Maybe this number will be even nicer, meaning closer to 1. Maybe you can try it with 2.7, etc., 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 right? So now, here is that important definition of that special number e. And let me just write it down right here, okay? Let me just write it down right here for you guys. Here is how we are going to have a really, really special number so that this quantity, this limit, is actually just 1. So here is the definition. We will say that, and I just want to have a special number so that when I put it into this base, right, this base, so the limit is equal to, the whole limit is 1. I'm going to use the symbol, and you guys know what the symbol is. Let e, which is kind of like a symbol, right? Let e be the special number, so I'll just write down be the number, so that when we take the limit as h goes to 0, and when we put in e as the base, we have e to the h minus 1, and then over h like this. Once again, e is this special number that will make this limit really, really nice, right? Special number for that base. We want this to be 1, and that's the definition of the number e. And we'll just make a real quick note right here for you guys. Notice that the number e is approximately 2.7182818 and so on, right? So this is that special number e, and in fact this is just one definition of the number e. The other definition of the number e is from the compound interest formula, all right? But this right here is for the derivative, okay? And in fact, perhaps many of you guys will tell me this right here, we actually know what this is. But remember, you must have the e first, right? You must have the definition of e first. This number, in fact, is equal to ln2, right? This is ln2, the natural log of 2. And this number is actually ln3. And this number right here, you guessed it, it's ln of whatever that base is, ln 2.5. And you can imagine that if you use e as the base, you would get the following. When we differentiate, let me just put this down, dx. Differentiating e to the x. This right here, we actually just get e to the x. If the base is not e, let me write down this right here. If we're just differentiating a generic base b, but this b has to be legit. It cannot be 1. It cannot be negative number, all right? Differentiating a number b to the x power, b could be equal to 2, 3, 2.5, etc. When we do that, you know the function part repeats, just like what we have seen, all right? But you multiply by this additional number, namely the natural log of whatever the base was, all right? So you have to do b to the x times ln b. So that's pretty much the idea. Now we can say that when we differentiate 2 to the x, the derivative of that is 2 to the x times ln2. When we differentiate 3 to the x, the answer is 3 to the x times ln3. Likewise, for 2.5 to the x, we get 2.5x times ln 2.5. So these two are the main formulas that you have to know, this right here, and also this right here, and one of the definitions of the special number e. That's it. Hopefully you guys like this video.
So good.